Impulse, momentum, and the impulse-momentum theorem is what I'm going to talk about now. Impulse, symbol J, is a vector quantity, and it is equal to the net force that acts on a body multiplied by the time interval over which that net force acts. At the beginning of this video lesson, you saw me leap off a table and land on the floor. The net force that acted on me to bring me to a stop when I hit the floor, multiplied by the time interval over which that net force acted, would be equal to the impulse on me. The unit of impulse is the Newton second. Momentum, symbol P, is a vector quantity, and it's equal to mass times velocity. My momentum changed when I leaped off the table and landed on the floor. There was a momentum right before I hit the floor, and then there was a momentum after I hit the floor, and that would be equal to 0 because I came to rest. Using Newton's second law, we can relate impulse to momentum, and it turns out that we get that the impulse is equal to mvf, the final momentum, which in the case of landing on the floor was 0, minus the original momentum, which would have been my momentum just before I hit the floor. So this is the final momentum, and this is the original momentum. So the change of momentum is equal to the net impulse. The unit of momentum, by the way, is the kilogram meter per second. This equation here is known as the impulse-momentum theorem. You can also use this to help understand why seat belts are advantageous in car collisions. You see, the change in momentum in a car collision is a constant. Just like when I leaped off the table and hit the floor. I had no control over my change in momentum. I had a certain original momentum, like a car before it hits a wall, and you have a certain final momentum, usually 0 in a collision. So you don't have much control, if any, over the change in momentum. But let's take a look at the impulse. If you wear a seatbelt, the time interval over which that change in momentum occurs is increased. Thus, the net force acting on you in that car collision decreases. When I leaped off the table and landed on the floor, what I did was I bent my knees, which increased the time over which the change in momentum, my change in momentum, occurred, thus reducing the net force on me. If there is no net external impulse acting on a system, it follows that the change in momentum, the linear momentum of the system, is 0 as well. Therefore, the original momentum of the system is equal to the final momentum of the system. This is known as the law of conservation of linear momentum. And it really is a result of Newton's third law. In a closed, isolated system, momentum is always conserved. Collisions. There are two types of collisions, elastic and inelastic collisions. With elastic collisions, both linear momentum and mechanical energy are conserved, that is, kinetic energy. We can write that the original kinetic energy is equal to the final kinetic energy for elastic collisions.
For inelastic collisions, momentum is conserved, but kinetic energy is not. Explosions. In an explosion, momentum, linear momentum, is conserved. What isn't conserved is the kinetic energy.